My name is Michael Celentano, and on behalf of Andrea Montanari, Yuchen Wu, and myself, I am presenting our paper, The Estimation Error of General First-Order Methods. Our paper is motivated by the existence of information computation gaps in high-dimensional statistics problems. In particular, in many problems, there exists a gap between what is known to be possible statistically and what is believed to be possible using an efficient algorithm. These gaps have been studied extensively by several authors. I've listed some references here. Our paper takes a particular approach. We look at a specific class of methods, the so-called first-order methods, and identify the optimal performance achievable by methods in this class. First-order methods are important practically because they are extremely efficient, running often in linear time, so they scale well to large data sets. I don't have time to discuss all of the models we address in our paper in this talk, so I'm going to focus on one model, the phase retrieval model. In phase retrieval, we would like to estimate an unknown high-dimensional vector theta, and we receive linear measurements of theta, but only get to see the magnitude of these measurements possibly corrupted by noise. A natural approach to estimation in this model is to use the least squares estimator, which is defined as the minimizer of this least squares objective. This objective is highly non-convex, so we may be concerned that it will be difficult to compute this minimizer. Nevertheless, we could imagine running one of our favorite optimization algorithms like gradient descent or accelerated gradient descent and hope that the output of the algorithm will still be a good estimate of the unknown parameter. These algorithms are called first-order methods because they access the objective only through first-order information about it, namely its gradient. It turns out that gradient descent is surprisingly effective in this problem. In 2015, Emmanuel Candes, Xiaodong Li, and Mahdi Soltanol-Khattabi showed that gradient descent achieves nearly optimal statistical rates in the phase retrieval problem. Since then, several papers have shown that gradient descent can achieve nearly optimal statistical rates in less time, with more aggressive step sizes, and with less careful initialization. The reason for this surprising success is that in the typical case, the optimization landscape is much nicer than it could be in the worst case. In particular, the gradient descent trajectory typically only explores a portion of the landscape which is strongly convex and smooth around the true parameter. This is an extremely important insight, but I want to highlight what makes it difficult to analyze this insight from a theoretical point of view. First, the gradient descent trajectory depends upon the data in a very complicated way. It repeatedly and adaptively queries the data, picking up more complex dependencies with the sample as the iteration runs on. Second, there is a large universe of possible modifications we could consider making to the gradient descent algorithm, which may enhance its performance or simplify its theoretical analysis. This makes designing an optimal iteration difficult and also makes it difficult to identify when an algorithm of this type is unable to achieve a certain statistical task or a certain statistical estimation error. These difficulties are particularly pressing in cases in which gradient descent algorithms fall substantially short of achieving statistically optimal rates. We don't need to look far for such an example. As soon as we make an assumption of sparsity on the unknown parameter in the phase retrieval problem, there is a gap between what is possible information theoretically and what is possible using known efficient algorithms. In particular, it is known that as soon as we have a sample size which is linear in the sparsity, we can achieve reasonable estimation error in the sparse phase retrieval problem. Nevertheless, for example, the thresholded gradient descent algorithm, which was proposed and studied by Tony Kai et al. In 2016, requires a sample size which grows quadratically in the sparsity. This quadratic dependence in the sparsity exists in all known guarantees for polynomial time algorithms. We would like to know whether this gap between a linear dependence in the sparsity and a quadratic dependence on the sparsity is fundamental, a limitation of our analysis, or a failure to implement appropriate modifications to the gradient descent iteration. Our paper sheds some light on this question. First, we provide a rigorous lower bound on the estimation error of a general first-order method, which is a class of methods which includes gradient descent. Second, we show that these lower bounds are achievable, and we specify exactly how to achieve them. Third, we show that in the sparse phase retrieval problem, there is a gap between what is achievable statistically and what is achievable with a first-order method. And I should mention that our results are more general, and another important application of our results is to sparse PCA, which is another high-dimensional statistics problem in which information computation gaps are conjectured to occur. Finally, though our results are already quite general, we provide a proof technique which we anticipate will be useful in studying similar questions in related contexts. To describe our contributions in a bit more detail, let me walk you through the major steps of our analysis. First, we move from thinking about the niceness of optimization landscapes to thinking about the structure of optimization rules. Let me show you what I mean. Here I've written the gradient descent update for the phase retrieval problem with a least squares objective. If I expand the gradient, we see that computing this update requires only two types of operations. The first operation is matrix multiplication, in this case by the matrix X, which is the design matrix, and I've highlighted that here in our formula. The next operation is the coordinate-wise application of a certain nonlinear function to our iterates, our data, or some combination thereof. It turns out that not only for gradient descent, but also for accelerated gradient descent, proximal gradient descent, many other first-order methods, and even algorithms that do not require computing the gradient of any objective function have this form, namely their updates require only matrix multiplication and the application of coordinate-wise nonlinearities. Our idea is to define a general class of methods, which we call the general first-order methods, which are defined exactly by having this property, namely they only use matrix multiplication and the application of coordinate-wise nonlinearities in computing their updates. This class of methods includes gradient descent, proximal gradient descent, accelerated gradient descent, in some problems mirror descent, and many other modifications of these algorithms. And it also accommodates ways of initializing the descent algorithm using an informative initialization. The next step in our argument is to argue that all general first-order methods are equivalent to an AMP algorithm after an appropriate change of variables. If you don't know what approximate message passing algorithms are, the main feature about them that is important for this talk is that their iterates are easy to characterize asymptotically. In particular, under Gaussian designs and under a certain proportional asymptotics, the AMP iterates are characterized by something called state evolution, which you can read about in the papers listed on this slide. Recall that one of the challenges in analyzing gradient descent and related algorithms is that the trajectories depend upon the data in a very complicated way. By reducing such algorithms to AMP algorithms, we handle such dependencies very gracefully. Because all general first-order methods are equivalent to AMP algorithms after a change of variables, finding the optimal general first-order method is equivalent to finding the optimal AMP algorithm. The final step in our analysis is to identify the optimal AMP algorithm. We rigorously show that the optimal AMP algorithm is something called Bayes AMP. To summarize, we show that Bayes AMP is optimal among general first-order algorithms. To be completely thorough, I'm now going to list all the major assumptions under which this statement is true. First, we assume that the measurement vectors in the phase retrieval problem are Gaussian random vectors. Next, we assume the coordinates of the parameter vector are drawn IID from a known prior mu theta. This allows us to incorporate structural properties like sparsity into our problem. Next, we permit that we have a possibly informative initialization in the form of a vector v correlated with the unknown parameter theta. Our results apply in a proportional asymptotics in which the sample size and the number of unknown parameters both diverge to infinity, and their ratio converges to a fixed constant delta. I should remark that the proportional asymptotics is a regime in which the sample size is always less than quadratic in the sparsity, so our results probe a certain portion of the conjectured hard regime in sparse phase retrieval. Finally, our results apply to a fixed, though arbitrarily large, iteration of a general first-order method in the proportional asymptotics. Because each update of a general first-order method requires linear time, our results apply to what is achievable by general first-order methods in linear time. To summarize, under these assumptions, we provide achievable lower bounds in the form of the estimation error of Bayes and P, and the estimation error of Bayes and P is, of course, achievable using Bayes and P. We can compare these lower bounds to statistically optimal performance, which in these Bayesian models is the Bayes risk and was characterized by Jean Barbier et al. In 2018. To make these bounds more concrete, now let me present some numerical calculations of the bounds in the sparse phase retrieval problem. Here I've assumed that we have a parameter vector with 20% of its coordinates being active, and we also have an L2 bound on the parameter vector. I've plotted here on the y-axis the maximal correlation achievable using a first-order method between the estimate and the true parameter. This correlation is achieved under a situation in which we receive vanishing amounts of side information, meaning we take a limit in which the amount of side information we begin with goes to 0. I've plotted this optimal correlation as a function of the measurement rate n over p, and we see that the maximal correlation achievable by a general first-order method is 0 below some threshold, which I call the spectral threshold delta SP. What is important is that the spectral threshold is exactly the threshold above which a general first-order method is able to achieve non-trivial correlation with the truth without an assumption of sparsity. That is, general first-order methods can succeed in sparse phase retrieval only when they can also succeed without an assumption of sparsity. General first-order methods cannot leverage sparsity in the proportional regime, which, as I said, is a portion of the conjectured hard regime in the sparse phase retrieval problem. Finally, I would like to emphasize that our results are much more general than just applying to the phase retrieval problem. In fact, we show that Bayes AMP is optimal among general first-order methods in a large class of high-dimensional regression and low-rank matrix estimation models. Another important application of these results is to sparse PCA. We show that general first-order methods cannot leverage sparsity in sparse PCA, and this is another problem in which gaps between what is possible information theoretically and possible in a computationally efficient way are conjectured to occur. Finally, we provide a proof technique which we expect will be useful in many other contexts. Let me remind you of the major steps in this argument. First, we move from thinking about optimization landscapes to thinking about update rules. We accommodate informative initializations and many modifications one could make to a first-order method by defining the class of general first-order methods. We handle the complex dependencies between the iterates of the general first-order methods and the data by reducing them to AMP algorithms. And we identify that the optimal AMP algorithm in these models is given by Bayes AMP. For more information about any of these steps and the other models we analyze, I encourage you to look at our paper. Thank you.